this is actually all live streamed, and I'm breaking it up into individual tutorial videos for YouTube. If you're watching one of these tutorial videos, for context, in the previous video, I went through setting up FFmpeg to decode an individual frame. Just so basically, how did I do that? So if I look at my load frame code, we start off by opening the file using AV format. Then we select our stream, like we unpack this file, and inside an MP4 file or an AVI or whatever the format is, there will be multiple streams. There will be an audio stream, there will be a video stream, there will be other metadata, there could be subtitle information. And I look only to find a stream that is a video stream. And once I have that, and once I know that I have a decoder for that, I set up my decoder to open up whatever data is coming in from AV format, and in AV codec, it's going to start decoding it. So we initialize that, and then we have this main loop where AV format will read a frame, we'll take a frame out of the, well actually we'll read a packet. We'll read a packet of data outside of the video file, and provided that this packet is relating to the video stream, we pass it into our decoder. We give a packet to our decoder, and the decoder will give us back a decompressed raw video frame. And that frame, what I'm doing now is I just unpack the luminance data of how bright or dark each pixel is, and I'm putting that into an RGB format by just putting the brightness as the R, the G, and the B, and as a result I'm getting this. I'm getting one image on the screen, which is a black and white image, because we don't have color data. So what I want to do now is, instead of just copying out the luminance of our decompressed frame, is actually converting the frame correctly to red, green, and blue so we can see everything. And the way we can do that is with a library called swscale. It comes along with FFmpeg, and all I have to do is just include it, which will be maybe libswscale slash, what is the things that I have to include? swscale.h, like that. I think that's it. Let me just check by running it. Yeah, that's the right include file. So we include this, and so at this point here, we have a variable. We have an AV frame variable called AV frame, like that, and that stores the raw data that's been decompressed by our codec, and it will store it in YUV format. So what is YUV? Let me just rely on Wikipedia here. So YUV is a color encoding system typically used as part of color image pipeline. It encodes color image or video taking human perception into account. So yeah, so this is a great example here. So we have a color image, and YUV breaks that image up into three components. We have the grayscale image of just the brightness, and then we have two components which together can describe all of the colors in the image. And so it's not quite hue and saturation. U and V are would look like this. So the value of U on this scale and the value of V on this scale will describe every color that you can get. The reason why it's split up like this and not described as red, green, and blue is that humans notice difference in brightness much more than they notice difference in color. So what you can do is you can get away with storing less information about color and storing more about grayscale, and humans will never notice the difference. So you can kind of compress an image just by changing the format in which you store it. So in the case of this raw video data, if I pause it here at the point where we've decompressed it, if I inspect my AV frame, I will have, so you see here, AV frame is the frame we received. It contains a property data, which has spaces, which has 8 pointers pointing to data. Only 3 of them are filled. So the first 3 contain in order the grayscale pixel data in position 0, the y pixel data or the u pixel data, and then the grayscale luminance pixel data y, the color u data and the color v data. Those are the free those are the free pixel buffers that we get out. Interestingly, how many bytes are there for each horizontal line of the video? For the luminance, there's 1,920 bytes for one horizontal line, which means that there's 1 byte for every pixel on that horizontal line, because this is a HD video, because it's 1,920 wide. But for the U and the V color components, there are only 960 bytes to describe one line, which means that every byte of color is split up into 4 bits for one pixel and 4 bits for another, if that makes sense. Like 1,920 bytes means you have 15,360 bits for the luminance data of a line. You divide that by the amount of pixels you have 8 bits per pixel. In the case of the luminance data, we put in 960, so you have 4 bits for the luminance. So actually we're storing half the amount of information for color than we are for luminance. And so that it's saving space by having it in a certain format. But for the presentation of that data, when we go into OpenGL, we want to store it in the format that suits the presentation, which is the display, and the display is RGB. We have a red, a green, and a blue LED, or we have a red and green and blue light emitting object on the screen. And by varying the intensity of those free lights, you will get whatever color you want. So we need to switch the format, and we can do this with swscale. So my old routine of just copying over the grayscale data, I'm going to remove that. I'm not going to use that anymore. Instead, I'm going to create a Scalar Context, which is all the data that the scalar needs to be converting color spaces or converting sizes of the image. So I'm going to say SWS Context, and we'll have our Scalar Context here, and we'll say we're going to get a context. We have to give it the width and the height of our video, so we have AV frame width, AV frame height. It's going to ask us for the pixel format, which our codec context knows. We can give it the pixel format. And what do we want to scale it to? What do we want to turn it into? Let me just show you get context. It has a few different things. It has source width, source height, source format, then destination width, destination height, destination format. So I don't want to change the scale of the image, so the destination width and height will be the exact same. But if you wanted to scale it down by a half, you could do that here. You could like divide the width there by 2, divide the height by 2, and you would get half the size image. So the software scaler can do that for you. The destination format. What do I want as my destination format? I want an AV pixel format RGB0, which means for every pixel that we have, I want 4 bytes. I want a red byte, a green byte, a blue byte, and then an alpha byte, which is just not used. But that's a very common internal representation for data, where you have 4 bytes for each pixel, where you have an alpha channel, where you can describe the transparency of the pixel. But here we're not going to use it, but we're going to get it to put it into that format. And okay, how do we want to do the scaling? So we have like the flags. We want to say we just want to do SWS bilinear scaling or fast bilinear. Let's do that. That's even better. It doesn't really matter because we're not doing any actual scaling, so it doesn't have to interpolate pixels. It just has to change color values. So I'll stick with that. It should determine that the width and the height is the same and that it doesn't scale at all. But that comes in handy when you're actually scaling. And then we have a source filter, we have the destination filter, and we have parameters. We're going to set all of those to null. We don't care about any filters that we're applying. That's our context. That's our scalar is defined to do that. And so now we just need to give the scalar the information to scale our data. I'm going to change this a bit. I'm going to say put width and height on the same line like that, like this. So that's the input width, height, and format, output width, height, and format, and then these options on the third line. If we don't get a scalar context, then something went wrong. We're going to say couldn't initialize swscalar, swscalar, and we return false. In that situation, again, we should actually close all of those inputs, but you know, error handling, I'm going to do that later on in this project. Right. If you saw, it's really annoying that when I pause the debugger here, that it is so, that the text is so small. I wish I could do something about that. But inside AVFrame, you see we have this data array with pointers to all the data and a line size array giving the information of how many bytes are in each horizontal line of data for each of those buffers. So we're going to give that to our scalar. So we're going to say swscale. We're going to give it scalar context, and we give it the AVFrame data, and we give it the AVFrame line size, and we tell it to start from the horizontal 0 all the way up to the height of the image. But then as the destination, we have to give it another one of those data and line size vector or data and line size arrays. So we have to create one. Now, unlike the input where we have 3 different buffers, we actually want everything to go into one buffer where each pixel is packed in, where you have the red, the green, the blue, and a 0 for one pixel, followed by a red, green, blue, and a 0 for the next pixel, red, green, blue, 0, red, green, blue, 0, until the end of the horizontal, and then we have red, green, blue, 0 for the next one. So we want to pack it all into one buffer. So we're going to tell it that. We're going to say, we're going to create a uint8t destination buffer, which will have our data. Did I delete that? I deleted that. Okay, so I need to allocate my buffer. Unsigned data pointer data unsigned char pointer. I'll use uint8t data buffer. New uint8t of AVFrame width times AVFrame height times 4. We're going to have 4 bytes for every pixel because we're going to have an RGB alpha. And so in our destination, we'll have that as our first buffer, and all of the other ones will remain empty like that. And then we have to have one vector describing all the line sizes, which will be 4 again. And the line size of our data will be whatever the width is of our frame times 4, because we have 4 bytes for every pixel. So the amount of bytes in the horizontal of our video buffer will be 1920 times 4, whatever the video width is times 4, and the line heights of all those other ones will just be 0. There's nothing in those buffers. So that's what we wanted to write the results into. So we're going to have destination, and we're going to have destination line sizes, and we'll see if that works. So yeah, let me just stop that and put a breakpoint after we do swscale and see what happens. Okay, so over here in our data, I see some stuff in there. So I see some data in there. That's really good. I want to see it on the screen. I don't want to just write it to disk or whatever. So let me first free the context. We don't need it anymore after we've scaled this one thing. The cool thing is, if you're processing all of this video, you set up your scalar once, and then for every frame that you have, you do swscale, and only at the end do you free the context. So when I start pipelining this where multiple frames will come in, then I need to manage these contexts properly so that FFmpeg gets set up once, and then we just run the functions for every new frame without changing any of the options. Yeah, so we've scaled that. I need to set, I want to set width out to the AV frame width. So for context again, if you're only watching this one video, I've got a load frame function that we're building here. And it takes a file name and it gives us back a width and a height and a data buffer. And so I just need to hand all of this back to whoever's reading so that they can put it into, so that they can read it. So I'm doing that. I'm going to free up all our resources and then return true that we succeeded in loading the frame. So let's run that, see if it works. Okay, that worked, but that's not a good frame. Okay, it's, I see. If I go to main here, we get our frame data back, and I'm telling OpenGL when loading in this frame data that it's in the format GLRGB, but it's actually in the format GLRGBA. So I'm telling it that the data that I'm giving it is RGBA, so it's actually 1 byte for the R, the G, the B, and then an A byte. It was misaligning it because of not knowing the format. There we go. Beautiful. So we have a properly decoded single frame from a video file going out of FFmpeg onto an OpenGL surface where we can project it, we can do whatever we want with it. If you think that seems like a lot of work to just get one frame, you might be right. But on the other hand, it seems like a lot of work to get one frame on the screen. But if you're going to build any program that's animating stuff and that's actually streaming video, you'll need to control all of these individual steps. You'll need to do different things in all these steps. Like, you see that we're like individually initializing the format context for opening up the file separate from the codec. But that's because you might actually want to treat the file in a different way, or only extract the audio, or have to extract both of them. So then you open your file, you get those two streams, and then you want to, when decoding packets, send them into your audio decoder and into your video decoder separately. So when it comes to creating an actual real-time video player, this would not be just one block of code. It will break up and it will actually touch lots of parts of your application. But for a single frame, this seems like a lot of work. But there we go. It would be cool to do some more work of like animating frames, but I'm pretty tired now. This has been a long stream, and I'm pretty happy that I can get one video frame on an OpenGL surface. Just let me change the file name and see if I can open a different file. Desktop, where are all my files stored? I have stream announcement.mp4 on my desktop as well. Yeah, really cool. Okay, I'm gonna leave it there. As always, all of this code is available on GitHub. You'll find it in the description. You can clone this. You can copy out any of the. You can use any of the code that you want. Yeah, I'm gonna check all of this in, and I'm done. Color. How do I say this? Decoding video data out and rendering. Decoding first video frame and rendering to window. push that. Okay. That's it for now. I'm going to leave it there. I hope I explained things in a way that is understandable, that you can get to work using FFmpeg now and you can start manipulating video files. Sometime next week, I will announce it. I will start animating videos on an OpenGL surface so that we can actually start seeing moving images, not just one image. But this is an important starting point where you see how an individual frame can be decoded. Once you know how to decode an individual frame, it's quite easy to then extend that to decoding multiple frames. The big challenge will then be when you're decoding all these frames, how do you synchronize them to the right frame rate? How do you understand when to render a frame? And so I will get into that in the next live stream. Thank you very much for watching. If you have, subscribe if you want to see more of these live streams, and I will see you in a week. Goodbye.